Welcome to This Explainer. Okay, today we're diving into one of the greatest, most stubborn, unsolved mysteries in all of computer science. We're going to look at how a massive collaboration of researchers has just used artificial intelligence to completely rewrite its own foundational mathematics. It's a really wild story of theoretical limits, cutting-edge machine learning, and code that literally evolves itself.
So I want to pose this question directly to you. What is the true speed limit of computing? We usually think about faster microchips or maybe throwing in more RAM, but the absolute limit of computing speed isn't just about the hardware we build. It's actually about the foundational math running our modern world. And the fascinating thing here is that foundational math might still have a hidden fast lane that we're only just beginning to uncover.
All right, here's our roadmap for today. We'll be hitting 1. The matrix multiplication engine. 2. The race for omega. 3. The optimization bottleneck. 4. DeepMind's machine learning approach. 5. AI evolving the code. And finally, 6. A new mathematical limit.
Section 1. The matrix multiplication engine, the heart of modern tech. Now, when we talk about matrix multiplication, we aren't just talking about chalkboard math from high school. We are talking about the core engine behind our entire digital reality. Matrix multiplication is the foundational operation that makes realistic computer graphics possible. It runs weather simulations, and perhaps most importantly, it powers the massive machine learning and AI models making headlines today.
The insights we're unpacking today actually come from a groundbreaking new paper led by researchers at Google DeepMind, working in collaboration with academic heavyweights from MIT, Columbia, and Carnegie Mellon University. And let's be honest, when this specific group of minds comes together, you just know they're tackling a fundamental, earth-shattering problem. At the absolute core of all this research is a deceptively simple concept: computational complexity. This simply refers to the minimum number of arithmetic operations. We're talking about the literal number of mathematical steps it takes to multiply large matrices together. Determining this absolute minimum is a major open question, and it's one that has remained stubbornly unsolved for over 50 years.
Moving on to Section 2, the race for omega, the 40-year mathematical sprint.
And that brings us to a very special mathematical symbol, omega. Omega represents the asymptotic matrix multiplication exponent. In plain English, it's the theoretical fastest possible time to multiply matrices. Back in 1969, a mathematician named Volker Strassen made a completely shocking discovery. He found that matrices can actually be multiplied faster than the standard cubic time method we all thought was the absolute limit. Ever since Strassen's breakthrough, the race has been intensely focused on shrinking this exponent, omega, as close to the theoretical floor of 2 as mathematically possible.
Now, the sheer difficulty of this race is just staggering. Take a look at the recent incremental, but honestly, truly monumental progress made over just the last few years. The bound dropped fraction by fraction, from Dwan in 2023 to Williams to Ullman, culminating in DeepMind's brand new record of 2.37117. These numbers might look like tiny decimal shifts to you and me, but in theoretical computer science, each one of these drops represents a colossal paradigm shift in our mathematical understanding.
But you're probably wondering, why are these improvements so tiny? Well, that brings us to Section 3, the optimization bottleneck, reaching the limits of old methods.
So those previous records we just looked at, they relied on refining a mathematical technique known as the laser method, specifically using a process called combination loss analysis. The catch? This analysis requires solving a massively complex, non-convex optimization problem. And it gets worse. As researchers try to dig deeper, increasing what they call the recursion depth to find better bounds, the complexity of the optimization grows doubly exponentially. It becomes a literal mathematical traffic jam that traditional software just cannot squeeze through.
I mean, just think of this massive equation as the final boss these researchers had to defeat. Previously, mathematicians were stuck using older, sequential software programs to try and solve this exact optimization problem. Because the math had to be solved step by step in a sequence, they simply didn't have the computational horsepower to push that recursion depth any further. They were completely maxed out.
All right, Section 4. DeepMind's machine learning approach, a new lens on an old problem. Instead of relying on traditional mathematical solver software, the DeepMind team looked at this pure theoretical math problem and decided to treat it like a modern machine learning task.
The scale of this shift is absolutely staggering. The previous state-of-the-art method was stuck at a max recursion level of 3, juggling about 25,000 parameters using those older sequential methods.
But DeepMind? They reformatted the entire problem into multidimensional tensors, which allowed it to run in parallel on modern GPUs using a framework called JAX. By doing this, they were able to push the recursion level up to 4, exploding the number of optimizable parameters from 25,000 to an incredible 7 million. They essentially turned a sequential math problem into a massive parallel supercomputing problem.
Section 5. AI evolving the code. When AI builds its own foundation. Because the team didn't stop at just using GPUs, they actually used artificial intelligence to improve the very math required to run artificial intelligence.
So DeepMind utilized this brilliant two-step approach. First, like we discussed, they addressed that massive optimization problem using gradient descent via JAX. That's a standard machine learning technique, and that step alone broke the world record. But then for step 2, they handed their optimization algorithm over to an AI agent called AlphaEvolve. AlphaEvolve's entire job was to act as a coding agent, continuously rewriting and refining that human-made optimization program to make it even more efficient.
Just to really ground the scale of what this AI was doing, consider this number: 5 hours. Every single time the AlphaEvolve agent wrote a new version of the optimization program, it took about 5 hours running on a single GPU just to execute it and output a new potential bound on Omega. The AI was literally evolving its own architecture, testing it, and iterating, generation after generation, to squeeze every last drop of efficiency out of the math.
Which leads us right into Section 6, a new mathematical limit. The record is broken.
By combining all this GPU parallelization and AI-driven code evolution, the record is officially broken. The new state-of-the-art upper bound for matrix multiplication is Omega is less than 2.371177. And to make sure this wasn't just some weird floating point computer error, the researchers ran a completely separate, highly rigorous verification step using exact rational arithmetic. They mathematically proved that the ultimate computing speed limit has indeed been lowered once again.
I want to wrap up on this incredibly provocative thought directly from the researchers' paper. They point out that while their AI and machine learning approach squeezed out a historic improvement, achieving much larger improvements will likely require entirely new mathematical ideas. Which leaves us with a pretty thrilling question. If human theoretical limits for finding these bounds have been reached, will artificial intelligence be the entity to discover those entirely new mathematical ideas next? Thanks for joining me on this explainer, and keep questioning the limits.